Today we're going to be talking about graphing absolute value functions using our transformations. We talked a little bit about transformations and how they help us with functions already this year, but we're going to start getting specifically into some of the different functions. So first, some vocabulary. The function f of x is the absolute value of x is an absolute value function. So if you look, you can see that the bars, those are the absolute value bars. It is a piecewise function, and so this is technically its mathematical definition. What it basically says is that if x is less than 0, we're graphing negative x, and if x is greater than 0, we're graphing positive x. And the reason being that if it's a negative number, think about it, the absolute value takes the opposite of it. It just makes it positive. So everything turns out to be positive. So if it's a negative number, we take the opposite of it, it becomes positive. If it's a positive number, it just stays positive. That's the idea with the absolute value function. This is a graph of what that function would look like, because again, for the negative numbers, we're switching them to be positive. So they have this negative x slope over here, and then on the other side, it's just staying x, and so we graph the line y equals x. So it is two linear functions basically put together. So it gives us this V shape, and it opens up. To the left of the line, it's negative x, and to the right of the line, it is positive x. It is symmetric, and that's important. Not all functions are symmetrical. This one is, though, and it is symmetric around the y-axis. It splits right down the middle. So there's some axis of symmetry that always goes through the vertex of the graph, and it is a symmetric shape. Some more vocabulary. The highest or lowest point on the graph, depending on which way your V is flipped, is called the vertex. That line that goes through the middle and splits it in half, that's that axis of symmetry. And it only has one axis of symmetry, and it does always have to pass through the vertex. So those are some important things to remember about the graph. So here are your parts. If we're going to graph this, we need our vertex. We have the actual V itself, that's the actual graph of the function. And then the axis of symmetry is not part of the graph, but it's just like an imaginary line that cuts it in the middle to show that it's the same on both sides. Now, here's some more vocabulary. The zeros of a function, if you remember, are where the graph or the equation is equal to 0. The function is equal to 0. And we know that that always happens on the x-intercepts. So the x-intercepts are the zeros. And so you can see, just like the parabola, the quadratic function, usually if this V is going to have x-intercepts, it's going to hit it in two places. Because just like the parabola would dip down and hit it twice, the V is turning around, and it is also going to hit it twice. So on this graph, we have zeros at -3 and 3. So a transformation changes a graph's size, shape, position, or orientation. If you remember, we had translation. That was shifting it up and down or left and right. Doesn't change its shape, doesn't change its size, and it doesn't spin it, so it doesn't change its orientation. A reflection is flipping it, so we can flip it, and then a dilation makes it bigger or smaller. And in the case of functions, we're generally talking about stretching it vertically or compressing it vertically. So let's think about the generic equation. If we take our transformations into account, we've got the absolute value of x, but these are the ways that we can change it. We can add or subtract something inside. We can add or subtract something outside. We can multiply it by a number, and we can make that number positive or negative. Those are basically your 4 transformations. So things that we want to remember is that that negative would flip it. So our V can either open up or our V can open down. The A is going to stretch it. So we can either stretch it and make it a skinny V by multiplying it by a number bigger than 1, or we can squish it and make it a fatter V if we multiply it by that number between 0 and 1, you know, 0.5, 0.25, 1/2, 1/3, something along those lines. H is that horizontal translation, so we're shifting it left or right. Remember, inside is always the opposite. So adding actually goes to the left and subtracting goes to the right. The other way to remember it is that we always do the opposite of that inside number. And then K is our vertical translation. We're going up and down. So when you put this together in a very practical way, HK is our vertex. That's what's shifting it left and right and shifting it up and down. So HK, just like when we did quadratics, gives you your vertex in graphing form. You do the opposite of the inside number, keep the outside number. So if we're looking at these different scenarios, let's take a look at what's going on here. So when I look at this one, it's adding on the inside, so that's going to move it to the left, and it's subtracting on the outside, so that's going to move it down. That's going to give me a vertex at -2, -3. So I have a vertex. This number here is stretching it. Now, these are straight lines. So when we talk about stretching it, we're really talking about the slope of those lines. So that means that I have a vertex at -2, -3, and then I'm going to have a slope of +3 on this side and a slope of -3 on this side. So we always do the same slope on both sides. One's just positive and one's just negative. So by multiplying by a number, you're changing the slope. That's what that vertical stretch or compress is doing. For this one, it looks like I subtracted on the inside, so I'm moving right and I'm moving up. So my vertex is going to be at 1, 2. We didn't do anything else to it, so its slope just stays 1 and -1. It's the exact same shape and it didn't get flipped. Adding on the inside, I'm moving left and I'm moving down. So that means I'm going to have a vertex at -3, -1. We did multiply by 2, so that's going to stretch it. So that means that my slope is going to be 2 and -2 on either side. And our last one, it looks like I moved to the right 2 and up 1. So 2, 1. I got two things going on here. I'm compressing it, so I'm going to have a slope of 1/3, so it's going to make it a fatter, squatter V. But we also have a negative. So that's going to flip my V. So my V, instead of going up, it's going to be going down. So it's going to be kind of a squat, fat little V, and it is going to be facing down. When we look at this example, again, important pieces of information. I'm moving to the left 3 and up 2. So I'm going to have a vertex at -3, 2. It is getting flipped. So it's going to be a down V instead of an up V. And I have a slope of 2 and -2. So now I know what my slope is. So I have a vertex at -3, 2. There's my vertex. I know I want my V to go down. So down how much? My slope is 2 over 1. So I'm going to go down 2 and over 1 in either direction. So down 2 over 1, down 2 over 1 the other way. Down 2 over 1, down 2. I can continue on down 2 and over 1 in this direction. Down 2 and over 1 in this direction. So that gives me a slope of 2 and -2. Don't forget, slope is rise over run. This one was negative, so it was -2, so we went down 2. And then just depending, we have to do both sides. If we do want to put our axis of symmetry on here, this would be my axis of symmetry, but you don't have to put that one on there. So we found our vertex and our intercepts. There we go. All right. So when we look at this one, what are our transformations? I'm going to the right one and down 2. So that's going to give me a vertex at 1, -2. This negative is going to flip it, and this gives me a slope of 1 over 2. It's -1 over 2 because it is flipped. So this is my slope. So I'm going to go down 1, and then we'll end up going left and right 2, depending on which direction we're going. But we have a vertex at 1, -2. And my slope is to go down 1 over 2. Down 1 over 2. Down 1 over 2. Down 1 over 2. Go back to the vertex. Down 1 over the other way 2. Down 1 over the other way. So down 1 over 2. It's a V, so we want to make sure that it turns out to be a V, but we do the slope in both directions. And that's how we get our v going in either direction. So our transformations get us our vertex, tell us whether we've compressed or stretched, and whether it's been flipped or not. Now, we can also work backwards and write an equation if we know what the graph looks like, because looking at this graph, it's a v. And because it's a v, then I know that its equation is an absolute value. But it doesn't start at 0, 0. So where did it move? It moved to the right 3 places. I know that to move to the right, I would have to subtract inside. So it moved right 3 spaces, and then it moved up 2 spaces. Opposite of the inside number, do the opposite of the first number, keep the second number, the outside number. Now, I need to figure out what is its slope, because if it has a slope of 1, I don't have to put any number here, but this one does not. For starters, it's facing down. I know most absolute value functions should be flipped, going up, so this one has been flipped, so I know it is negative. And then what is my slope? Well, let's see. It went from here to here, so it went down 1, 2, 3, 4, and then it went over 2. So down 4 over 2, down 4 over 2, that's going to actually be negative 2. So we've got a slope of negative 2 out here. We have our transformations, and that gives us the equation for that graph. Looking at this one, again, it's a v, and it's facing up, so I know it's a positive absolute value of x. But how is it moving? So it's not at 0, 0. It moved left 1. To move left, we add on the inside. Then it went up 3. So it went up 3. It is positive, so it's going up. And then let's see exactly what did we move here. We went up 1, 2, 3, 4. And we went over 1, 2. So it has a slope of 4 over 2, which is 2. It is a positive 2 slope. So that gives me my slope. And I have the equation for this graph.